Welcome to Cyclopod, showcasing work by early career geoscientists that is of interest to the cyclostratigraphic community. This podcast is made possible thanks to financial support of the International Subcommission on Timescale Calibration.
Hi there, and welcome to the 16th episode of Cyclopod. As usual, I have Anna Joy here at my side. Anna Joy, how are you doing?
Very good, and Happy New Year.
Happy New Year.
It's nice to be here in person.
Our guests are Pierre Josso
and Tim van Peer.
So Pierre Josso is Deputy Director at the Critical Minerals Intelligence Centre of the British Geological Survey here in the UK. Pierre, you obtained your PhD in geochemistry from the University of Southampton, and you are listed here as an expert in ferromanganese deposits. Is that correct?
Oh, hello everybody. Yes, indeed, it is correct. I've been working on deep sea deposits for the last 10 years. I've been studying all the parameters that influence their chemistry, their formation and preservation on the seafloor.
Really cool. So thanks, Pierre. So also joining us is Tim van Peer, who's an IDP research fellow at the University of Leicester. Tim, you work especially in paleomagnetism and cyclostratigraphy, especially focusing on paleoclimate around Antarctica. And currently within IDP, you also look at downhole logging and play a role in mission-specific platforms.
Hi, thanks for having us. Yes, it's exciting to be here and to chat to you. Yeah, it's quite a lot of things I'm doing at the moment, I guess. Lots of things going on at the same time. It's exciting to work on Antarctica and ocean circulation and apply the various relevant topics to it and figure out what we can learn from it.
So today we're going to discuss a paper that is already 3 years old, but both Anna Joy and I thought it was exciting enough to still have an episode for Cyclopod about it. We're going to look into the Milankovitch cycles that are recorded within a ferromanganese crust, so a rather atypical geological archive or paleoclimate archive. And we're bringing in two different sets of expertise here with Pierre and with Tim. But before we delve into all the details of the Milankovitch cycles, Pierre, can you tell us a little bit what are ferromanganese deposits and how do they form at all?
Okay, yes. So those deposits are quite interesting because they are one of the three main classes of what we call deep sea mineral deposits. You got massive sulfide on one hand, polymetallic nodules, which are quite common in the Pacific Ocean. And the last class that is being studied as well is ferromanganese crust deposit. So those are basically chemical precipitates that form by the accumulation of iron and manganese oxide which are dissolved into the ocean, and slight variation in the oxidoredox potential of the water will make some of it precipitate. We're talking about a very, very slow process on the order of 1 to 5 millimeter per million years. So it's actually one of the slowest processes on the planet, slower than plate tectonic, just to give a perspective on things. And effectively, those oxides are really, really reactive in seawater, so they're really good at scavenging all the other dissolved elements that make up the chemical budget of the ocean at the time they precipitate and accumulate. So some of the work that I've been doing was to use those archives as long-term records, really, of the evolution of the ocean over the Cenozoic. And that's why those deposits are quite interesting.
Yeah, but from our paleoclimate perspective, of course, they're not your typical sedimentological archive, right?
Well, we're talking about a resolution which will be very, very different. We're talking about long-term trends, what we see over millions and millions of years. And I think this is one of the really strength of that study that we managed to publish with Team, is that the discovery that effectively we can bridge those two areas of science and effectively join the mineral resource aspect and the understanding of how climate, oceanography combine with astronomical parameters to influence the chemistry and the isotope records of those deposits at the highest level of resolution in those mineral deposits.
Brilliant. Two worlds colliding there. Because, with these records, you've got quite a lot of challenges going on, from anything from how you actually date them to, how you can kind of integrate them with other records. So how has this been approached in the past?
So these deposits have been studied really for paleoceanographic archive for roughly 30 or 40 years. In various places around the globe, we've had a lot of really good archives from the Pacific Ocean, but also from the Northwest Atlantic, where some of those deposits have been studied to explore evolution of glacial interglacial cycles, the influence of the glacial retreats on the budget of sediments going into the Labrador Sea. So we're commonly playing with 500,000 year resolution for those deposits, which for a geologist still remains like a snapshot in time. But for cyclostratigrapher, I understand that this is already not so good. It's been a long study, and we've come a long way on developing this methodology. And another big improvement that these results have shown is that we can actually improve the dating resolution by at least 2 orders of magnitude. It's important to understand that these deposits are very difficult to date. The most common isotope radiogenic isotope dating methods do not necessarily work because it's an open system. You're constantly rebalancing your crust with the seawater, so you cannot use strontium or neodymium dating or uranium thorium for that matter. So usually we have a fairly inaccurate way of dating those deposits. Another funny aspect was, how do we get your hand on those? So we developed a new method to recover a really good archives. So these deposits are really nicely stuck to the rock they're forming on. So we had to drill. Obviously, they're not really thick deposits. And we developed a tiny ROV-mounted drill during one of our expeditions and recovered a 20 centimeter core that was presenting us with a nice 5 centimeter basement, carbonate basement with a 15 centimeter thick ferromanganese crust sitting on top of it.
Yeah, but now I'm intrigued, Tim, how did you get involved in this story then? It doesn't sound like an archive that a cyclostratigrapher is waiting for.
It was quite a surprise. So Pierre and I were PhD students together, so you talk about what you do and what you work on, and we just, for sheer fun, trying to figure out whether there was a theoretical possibility for us to do a project together. So we sit in the pub and we have a good time, and we realize actually that there may be potential, because Pierre found these odd patterns, these odd cyclic rhythmic patterns in a data set he'd been working on. And it didn't really make a lot of sense, because just trying something, and I'm sure he can tell much more about it, how it exactly went. But he came with this data set to me, and I was like, actually, after sitting down and looking at it, this has a lot of potential. There's a lot of good stuff in here. Let's explore this further. So we did. So he gave me this lead isotope data set, and we kept going back and forth a few times to figure out, whoa, we can really push this pretty far.
Yeah, that's cool, because we have here a piece of crust in front of us, and it is nicely laminated. Do I understand that correctly, that in theory you could use such a crust to have an entire record of Cenozoic's deep seawater chemistry?
Yeah, effectively. So the core that we decided to work on for most of my postdoc was obviously one of the nicely most well preserved, and used to show one of the longest record. So I did a full set of dating using various indirect methods, and we actually realized that the base of the crust was 76 million years old, and it was extending, providing us with a near complete record. Roughly 45 million years worth of data was recorded within those 15 centimeters, And a few hiatuses here and there, which we nicely correlated to some of the other major transformation of the Atlantic circulation and other paleoclimatic events. But that's another topic of discussion potentially. It was quite an interesting sample, because it shows very nice mineral texture as well into the interval we studied in detail. And we had an opportunity really to tie those changes in both geochemistry, isotope data, and mineral texture to potentially orbital cycles and climate. So the way really we come around to this data set is that I was initially zapping my samples with a laser to produce rapid transect of lead isotope data, which are very useful to correlate your sample stratigraphy. And I was not at all looking at producing something of that resolution, but when we started looking into the detail, we were seeing something in the data, effectively, as Tim said.
Oh, that's really, really quite cool. And so were you on board when you collected? Were you part of the expedition that collected these? And did you have any inkling when you got this sample of how cool it would actually be?
Well, that takes us back to 2016, really, because that was the JC142 expedition from the Marinetech project, which was my postdoc. So I joined the board and really was sampling and directing the sampling of the expedition for recovering the sample I would use for the geochemistry on those mineral deposits. And it was a really fantastic opportunity to recover some quite unusual samples, because most of the time those ferromanganese crusts are recovered by dredging, which is quite a dull, imprecise way to recover samples. Sometimes you may have blocks that have fallen from the summit of a seamount that went down all the way down the slope. So here what we did, as I said earlier, we kind of deployed this tiny drill, and we were able to recover a fantastic sample set from the summit of Tropic Seamounts, which is a submerged volcanic edifice which is lying really halfway through between Cape Verde and the Canary Island, about 500 kilometers off the coast of Western Africa. So fantastic expedition.
Yeah. So any inklings of whether that particular sample would be as magical as it's turned out to be, or was that more something that came as you kind of delved into the methods?
Well, a bit of both, because we knew from the beginning it was one of the thickest samples that we had recovered, so obviously it held a lot of potential. But with those things, as for nodules, any iron manganese oxide deposits, the depositional rate can vary by a few orders of magnitude. So actually samples that may present the same thickness may represent completely different periods of deposition, and also the amount of time that they will actually represent. So that was another finding from using the lead isotopes, that we were capable of evaluating changes in growth rate between region of that seamounts that were separated by just 100 or 200 meters. But effectively, we already knew these samples would have a lot of potential.
In terms of the technique, you mentioned was zapping, as you quite nicely said, zapping away at your sample. So this was laser ablation multi-collector ICP-MS. Is this a well-established technique, or you guys really kind of went to town on this in terms of pushing the boundaries of what could be done, right?
Yeah, there's a 2 micrometer resolution. That's amazing.
Yeah, effectively. So laser ablation is quite a common method for studying mineral deposits. You always need quite a high resolution for studying the mineral interface and getting the chemistry of those tiny grains. But where we did a lot of work was effectively after realizing there was some potential interesting signal hidden into our long-term high amplitude, fairly low resolution first pass on the data set, we went into the development of modifying the shape of the laser. So usually you have a spot, so a circle, but we used a laser that was able to modify the size and the dimension and the shape, the geometry of its slit, and we used what we call a letterbox format. So those samples are finely laminated. What we try to do is obviously find the sweet spot between optimizing the signal, the quality of the data that you can acquire but not compromising the volume that you're ablating as well, because you're trying to measure with the best resolution possible. So we compromised for a 2 micrometer by 150 micrometer letterbox format, which gave us quite a lot of across laminar volume, but within laminar resolution. And roughly, if you compare that to the initial growth rate that we know about those rocks, 1 to 5 millimeter per million year, then this 2 micron resolution gives us roughly a point every 1 to 5,000 years old. So effectively, that was the first time laser ablation was employed in this way in those deposits, because we never thought it would be possible to get down to seeing such a small, high resolution, high level signal.
Yeah, without smoothing it, which is
really
without
incredible.
smoothing
it. And so, if I understand correctly, you ended up with this super high resolution lead isotope series, that series, and you saw some oscillations in there, right? And so you immediately realized that you needed a cyclostratigrapher for that?
Well, I obviously, when I saw the signal oscillating in front of me and with some pattern I only knew I had seen before in my university years, I thought, well, there is a lot more to that study than I can probably finalize by myself. I need some people that know what they're doing with those kind of signal.
That's where Tim comes in.
Exactly. and it was a fantastic thing, because it threw us back to effectively PhD years when we were discussing our respective science and how effectively in the future we could collaborate. I thought, this is the key. I have the data where we can finally do this study together. And working on this deposit and trying to improve the dating, the method, which are quite inaccurate, I saw straight away that this was our avenue for improving and getting a big impact on the science.
And so, Tim, you weren't afraid of delving into that controversial topic, maybe, or how did you go about in analyzing that series?
I think if you get a data set like this, you don't consider it controversial, and when you look at it and you're like, I can just see the precession and eccentricity cycles in there. They were just jumping out at you. And I printed out the data set and I started scribbling on it, and I was like, okay, I can just count the precession cycles. I can see the eccentricity modulation. And then I realized, actually, wait, let's take 2 steps back. I'm talking to people who probably have never done this before. Everything I'm drawing here, I need to explain to them. So I could go through all the different steps of how we would do with cyclostratigraphy and astronomical tuning. We could do this together, because we were just exploring, what can we do? Can we go further, older, younger? And I could just make observations and say, look, this is what I see, this is where we can base the evidence on, and these are the statistics we need. And it just worked brilliantly.
So did you have the full data set at your disposal, or was it a little bit of the data that you saw initially?
I have to say that a lot of the end result was from Tim pushing us to produce better data and longer data.
More and more and more.
Yeah, so Pierre sent me this data set and I was just really excited to look at it. But at the same time, it was only 2 millimeters long, and it just everything I was used to in thinking about spatial patterns, everything had to be revised into micrometers and millimeters. But I'm working on a 2 millimeter interval, started counting cycles, and you count I don't know, 20, 40 cycles or something in that really short interval. It's really exciting to work with. And I was like, well, actually, I only have maybe 800,000 years, 2 long-term eccentricity cycles. Isn't there more? Can I have some more, please? So I went to Pierre. I was like, can I have some more, please? So we did. Yeah. And I passed the buck back to him with like, good luck. What can we do?
Yeah. And so in the end, in the paper, you have a 7 millimeter record, correct?
Yeah, effectively. So it was kind of constrained by also natural variation in the mineral texture on what was present below and above that interval, and we really pushed the capacity of the laser to produce a continuous record of the 7 millimeters at that level of resolution. That was 2 or 3 complete days of continuous analysis for the laser, so you have to be conscious about that as well. But
I was just out of curiosity, how many data points did you generate in those 3 days?
Oh dear, I don't know. Probably hundreds of thousands.
Wow. That's a good data set to work with.
Good to do statistics with.
Yeah, definitely. Yeah, so Tim, you mentioned, that you could see the cycles in there, but how did you go about convincing everyone that this was real?
The record looked so gorgeous that I really want to make sure that I spend a bit of time on it and to go through all the different steps to convince myself that it looks good. So the first step is just purely does it look like something I can recognize? That step was kind of straightforward because the data just shouted at me more or less, like, look, I'm worth investigating. So sure, we'll go ahead with that. Chatted with Pierre about, can our signal be reliable? What kind of tests do we need to do to make sure that we really have a reliable isotopic ratio? That turned out to be all good. So we tested, for instance, whether there's a relationship with the total lead concentration. Could it somehow modify our isotopic ratio, distorted in a way that we see some coincidence in terms of patterns? Well, that turned out to be all good. Made sure we tested the crust and repeated our measurements over a smaller interval, so we know these cycles are actually repeatable across the entire crust and not just a coincidence of one trace. And I was like, okay, actually, these cycles look pretty real. Let's see what we can do with this. And then I went back to my cyclostratigraphic training, and I just went through all the different steps that are now outlined in the literature as well. Like, just start drawing on it, identify which cycles you see. And I was like, well, actually, I see this kind of, these patterns are recognized as precession and eccentricity, and I can just draw them on this isotopic record. That looks really good. Okay, let's do a wavelet, let's do a power spectrum, let's do filtering, all the standard techniques we use. And I was like, well, actually, this is all in that domain. It still looks good. What can we do next? What can we do? This is all in terms of observations, but I realized we need to do this statistical testing as well. So what do? You throw it in time opting, you see what comes out of it, and suddenly you realize, actually, this is statistically significant. This looks really good. Mm-hmm. And I hadn't even started on any analysis in time domain yet, which then became the exciting bit. Could do a floating H model. Realized that, and in the meantime, everything kept lining up. It was still precession and eccentricity.
Yeah, and that's really cool, because the sedimentation rate that you came up with by using time-up, Pierre, you were very happy with that, right?
Yeah, I was very happy because it matched the growth rate that I could derive from two different methods that I had that were also independent. So we had on one hand cobalt chronometry, which correlate the geochemistry of the deposits to its accumulation rate, and on the other side I had osmium isotopes, which also allowed us to have a very clear dating of the start of our record just after the meteoritic impact, which makes a big isotope dent in your record. So this is why also another reason we choose that portion of the sample is that we had a very clear marker to say this is the start date. And then Tim came along and effectively presented me with data that was fairly consistent, showing exactly the same trends at the same time within the same range. So we're very happy with that.
Yeah, and you say start date, and that is really cool, because you guys, you've not only been able to make a floating H model, you actually anchored it in absolute time. You tuned the record, or you made a absolute H model. How did that happen?
So with the osmium shift at the KPG boundary, that was a clear marker. So we knew we were just at the start of the Cenozoic. We knew our record wouldn't span across the KPG boundary, but just beyond into the Cenozoic. And it's like, okay, let's take its high point. Let's look at the astronomical solutions and let's see what we can do. Again, in this exploratory fashion, because I was trying to talk to geochemists who've never done astronomical tuning before. What can we do? How far can we stretch it? How can I convince them that what we do is actually realistic? So Pierre gave me two tie points with about 500,000 year uncertainty each, and somehow it fitted in just perfectly. I looked at the eccentricity signal we could see in the lead isotope record, looked at the different available eccentricity curves for that time interval. Yeah, we know there are some uncertainties, but generally the overarching structure is the same. So I could start to tie the eccentricity signals I could recognize in the lead isotope data to what was available in the eccentricity curves, and it lined up perfectly. So then the growth rates I got from my floating age model, when I turned them into absolute growth rates and absolute ages, still lined up perfectly with the growth rates that Pierre had collected.
Yeah.
And I think one other potential really supportive information that we had is that suddenly we started seeing major correlation as well with the mineral texture and the age model that you had produced, and that was also a big revelation.
So, but maybe Pierre, when you say texture, what exactly do you mean? How do our listeners need to picture that visually?
Right, absolutely. So imagine your precipitation of your iron manganese oxide is like snow falling over a mountain, and snow accumulation will obviously take different shape if you have a lot of wind, if you have a very rocky terrain, or if it's your flat plain. It's a bit similar for iron manganese crust in the ocean, and depending on how much background sedimentation, if you have also a very strong current at that time, your accumulation of iron manganese oxide will take slightly different shapes. So we have in this interval an alternation of very nice laminar structures which are alternating with much more columnar, debris-rich intervals.
Oh, fascinating. And how did that? Could you see these textures relate to any particular phase in eccentricity?
That was the big surprise from this, and at the same time also a bit of the challenge I faced whilst doing the cyclostratigraphy and astronomical tuning, because those laminar intervals are really nice. You can just recognize every single precession interval. But every now and again, this columnar interval comes by, and I'm like, suddenly the laminae are gone. You don't recognize the nice patterns anymore, and you have to look carefully what's actually in your signal and what's there and what's not. What I realized, those intervals where the laminae were, I could really clearly recognize individual precession cycles and the eccentricity modulation from both 100 and 400 kiloyears. And then when I fixed that into a tuning, I realized those columnar intervals actually occurred during 400 kiloyear eccentricity minima. So I was really surprised how that actually ties in. So maybe there's some kind of feedback related to the short-term eccentricity cycle. Maybe there's relates to differences in precession. We don't really understand where or what's the key driving mechanism there, but the observation stands that these columnar intervals occur during 400 kiloyear eccentricity minima.
It's time for the number of the month. And this month the number is 50%. In 2023, globally we've seen a 50% increase in renewable energy. I think everyone in this room is very happy about that. Pierre, what do you think is the role of geoscientists in this transition towards a green energy?
Well, I think we are obviously acting and working in a primary sector that supports every other industries on the planet. I'm mostly talking on the mineral exploration side of thing. Everything that we have around us is made of material that have been extracted from the ground, and obviously as we transition away from fossil fuels, we are getting into a much more metal-intensive society. And I think, obviously from the mineral side, we're going to need more and more people that are capable of finding new mineral deposits and having an understanding of the environment to make that exploitation sustainable and much more environmental friendly. Obviously, geoscientists on all the other disciplines will have a key role in understanding how water can be managed properly. Geophysicists will have a key role in understanding how to better build our cities and use our material, and plenty of other examples likely, really. So
it's still a good time to be an earth scientist in general.
Oh yeah.
So you mentioned geophysics, geophysicists and the role that important role they could play in upcoming energy transition. Tim, you're a geophysicist by training. Any thoughts?
Yeah, certainly. If you look at the current role I'm in as a petrophysicist at the University of Leicester, the field originated as an oil and gas heavy field. Like all the studies were done on that, trying to understand the balance between gas, liquids and solids, and trying to figure out where the best reservoirs are. Nowadays, petrophysics is moving away from that into much more the renewable energy side. If you think about building a wind farm off the coast of wherever you want to build it, you need to do those sub-bottom studies to figure out where it's actually safe and sound to build, let alone to do the preliminary investigation, site survey work to make sure that you don't accidentally build up some kind of munition dump from whatever war we faced. All this kind of exploratory work, we need to make sure we do that in a safe and secure fashion. So there's a lot of work to be done from a geophysical point of view to prepare for what the future brings.
So back to the science. We have an oscillating lead isotope pattern. We are all convinced it's driven by Milankovitch, but what does it actually mean in terms of climate and ocean processes? Like a change in the local lead isotope reservoir can have multiple causes. So Pierre, can you enlighten us a little bit? What are potential drivers of lead isotope changes in the Atlantic Ocean?
Sure. So very briefly, lead isotope is very nice because it's not subject to fractionation from biological or temperature processes. So we're really looking at physical processes that mixes two different reservoirs. So we have a change, an oscillation between two signatures. What's different? What's changing? So some of the potential hypotheses that we had was to verify that we didn't have any volcanic or hydrothermal input, which have a very different signature in lead. We could rule that out because obviously the largest volcanic eruption that happened at the time was the eruption of the large igneous provinces in the North Atlantic, but they were quite a few million years later, so we could rule that out. That was a really good validation. Then hydrothermal signature, we still are within a seamount chain, which is quite active, but having this frequency of potential hydrothermal activity over such a prolonged period of time was very unlikely. We've never seen that before, so we also quite confidently rule this out. After that, we have obviously the elephant in the room. We have a new water mass with a different lead isotope signature that is coming periodically. But tectonically at that period, the North Atlantic was fairly stable. There wasn't major opening of oceanic gateways. We didn't see glacial interglacial cycle that could completely change the water level and so on. So obviously we also considered that changes in water masses were very unlikely from a mixing of two potential lead members. So then the next thing that we need to look at for lead, which is very relevant for this isotope system, is where does the lead come from in the ocean? And the next best thing is weathering from continental masses. And then lead, therefore, after that becomes a bit complex. It's a complicated system, usually connected to, obviously, radioactive decay of uranium, thorium-containing minerals. So you can have incongruent weathering and radioactive decay. So that would be related whether it's a physical or a chemical weathering of your continental source, or the other alternative was whether, similar to the ocean water masses, do we have two competing sources on land that come into play at different times or in different proportion? And this is what we really explore with this with the model.
So all of this really pointed quite strongly in that you could be confident in that the variation you saw in the lead isotopes was reflecting changes in the source region and the weathering of different source regions in West Africa. So we're talking here Paleocene. What did this tell you really about what was happening with West African climate at the time?
The nice thing here is that we understand the overarching geology of Northwest Africa reasonably well. We can map out the big terrains and what kind of expected signal they would provide in terms of provenance into our crusts off the coast of Northwest Africa. And then you can start to plot around, well, if the ratio goes up or down, which terrain would likely be providing more signal than the other, and what would be the process driving this change in provenance. And then you start to think about the monsoon quite quickly. What kind of precipitation or maybe droughts or what kind of patterns do you get out of that? And if you think about the modern day world, or at least say on a geologically modern day world, you think about the African monsoon and all the effects it had on the wide area. If you think about the Mediterranean, for instance, with the classical records there, that's where I was trained as well. So you get that link was made quite quickly and quite easily. And I started to explore, well, okay, so what if we start moving, say, the ITCZ on precessional timescales like we would see in a modern day geological setting? That lines up really nicely because you start to activate these different terrains. And we looked at the history of Africa and its latitudinal movement. It shifted a little bit, which actually worked in our favor to push those terrains into the right regions for what could be the case for the Paleocene or the early Paleocene, to be precise. And then you can start to think, okay, well, maybe we see these patterns. We get a bit more precipitation on one part of the cycle, a bit less on the other part. And suddenly you can start to think about the phase relationship there with full understanding of what actually been going on in terms of lead isotopes.
What phase relationship did you then see with the different regions? Was there a particular region that really sprang out?
So effectively, the geology of Western Africa is dominated by the emplacement of two cratonic units, which are dated Precambrian and Archean. So very old rock, lots of radiogenic material, so lots of a very strong radiogenic lead M member. And those two units are separated by the Tawadeni Basin, which is a major dust source, which also fit nicely with some of the previous studies that we've heard on that podcast. And actually is made of very different types of material, more your classic dust or sand area, which will have a much more common lead signature. So those were the two end members we were looking for, that we were planning, and effectively, as Tim said, shifting the position of the ITCZ, bring the Tawadini Basin with its more common lead signature into play a lot more during the high insolation periods. And what was really interesting is that we could tie as well not only the lead isotope signature, but also the geochemistry of the crust, which was at those periods much richer in iron, aluminium, silicon, and titanium, which are obviously clear marker of a higher sediment detrital input.
Great.
That's fascinating. And when Earth is in the perihelion during boreal summer, you're actually bringing in that less radiogenic detrital material, and at the same time you find high silica, high aluminium, high titanium, high iron in your ferromanganese crust. That's amazing. But you went even one step further and you established a mixing model, and because we know from the modern world that these precession-driven variations in precipitation can go up to 50% sometimes. But your mixing model shows that you actually only need like a few percent shift between the two end members, radiogenic end members, to explain the patterns we observe in the Paleocene ferromanganese crust, right?
Yeah, so obviously this mixing model takes into account a few working assumptions. We had to consider that the two geological domains had fairly similar initial concentration in lead, because obviously that it's a mixing model, so you would otherwise need to work this out. And we estimated, using modern day analogs from studying the sediments in the tributaries of the Congo River and its sediment fan as well, we could work out which terrain was producing what kind of signature. And that allowed us to create the end member point of our mixing model. And obviously our data fit right in the middle, which is a good confirmation that we've chosen the right analogs for this. And effectively, the amplitude of variation that we saw into the lead isotopes represented roughly a 2 or 3% change in the contribution of the more common lead end member. It's important to understand as well that the more radiogenic, so the cratonic Archean terrain, were still constantly being weathered because they were in the equatorial belt. It's how much more you bring of that additional end member to the
a bit of dilution, sort of.
Effectively, yes. So 2-3% of additional contribution to generate that variation, when you know that you can have between 15 and 50% changes in precipitation over a region. That seems fairly convincing. It's the right order of magnitude we were looking for.
And it fits with our understanding of how the ITCZ actually works and in response to precession. So
it's really convincing to see that, this relationship that you see between these source regions and radiogenic lead was also captured in other geochemistry. But could you also see it in the mineral texture itself?
Well, yeah, effectively, that was one of the strong hypotheses that tied up nicely, because it's understood that columnar texture usually happen when we have a much higher detrital input into the ocean. So effectively, having this concomitant with the period where the sedimentary basin was solicited a lot more by the precipitation, then completely ties in directly. We have an alternation from equatorial weathering, nice laminar structures, and then we move into this higher regime, hydraulically speaking, much more input from sedimentary system, columnar texture, perfect match.
Brilliant.
Yeah, and that is a fantastic conclusion for this podcast. Tim, Pierre, we thank you very much for all these insights in that fantastic paper that came out in EPSL, by the way, in 2021. But of course, we're not letting you go before knowing how you're going to continue in this topic. I mean, I think you have some gold in hands, right? Well, iron and manganese mainly, but...
Well, I think what this study has demonstrated is that both our fields can bring a lot to each other, and effectively this is a collaboration that has a good future, I think, and we're already capitalizing on it in a sense that we're already working on developing those astronomical solutions for other records that I'm studying for other projects. We have one project in common with Team, and I'm fairly sure that Team also probably has a lot more ideas on how to bring that into more into his area rather than valorizing the mineral side.
We can really have a big range of possibilities. One of the things that Pierre highlighted early on is the great amount of effort it took to get this record together. Are there ways we can simplify this or automate this? Can we take shortcuts without compromising quality? Those kind of questions are practical method questions we're trying to answer. And at the same time, as a cyclostratigraphic community, we're trying to simplify our methods where possible without compromising on quality. Where can we go from our side as well? But at the same time, wider implications. We've seen that our field is developing so quickly. Imagine if we could apply this method for the entire Cenozoic and we just get this across the entire Atlantic Basin. Get all these kind of 2, 3, 4 million year snippets all together.
Stacked ferromanganese deposit.
Imagine, you can just correlate every single lead isotope curve from one place to the other. And then imagine the next geochemical proxies you can do. Think about your traditional suites of proxies that are suitable for an iron manganese crust. So much we can do.
Oh wow, that's sounds like you guys will be kept very busy in future. And it's really great to see the two quite different fields coming together and really pushing the boundaries far at the interface of your respective sciences. New dating and some exciting prospects for both fields. So thanks very much for sharing that with us today in person. It's nice to do this in person. And looking forward to seeing everyone at the next Cyclopod.